Welcome back. In this last segment, we introduced the Big-Theta notation, which is an extension of the big O and the big omega notation. Assume that the function f of n is big O of g of n. Then we know that g of n is an upper bound on f of n, which means f of n does not grow any faster than g of n. However, this upper bound may not be tight, meaning that g of n may be a very poor approximation of the n behavior of f. Let's consider the function f of n equals 3n plus 1. Clearly, this function is big O of 3 to the power n. However, this upper bound is not a tight upper bound at all because it grows extremely fast since it's an exponential function. In particular, it grows a lot faster than this polynomial of degree 1, which we know is big O of n. So in order to get a clearer picture of the n behavior of a function f, it is usually helpful to have both an upper bound and a lower bound on the rate of growth of f. In particular, it's extremely helpful when the upper bound and the lower bounds are the same function, g of n. And so this concept is exactly what we call the Big-Theta notation. So now let's give a definition of that concept. As always, let's assume that f and g are functions from a set of numbers like the integers or the real numbers to the real numbers. We say that the function f of n is Big-Theta of g of n. Now this symbol here is the Greek letter theta in uppercase. So f of n is Big-Theta of g of n, or equivalently we say f of n is of order g of n, meaning f grows at approximately the same rate as g of n when n is large enough. If and only if f of n is both big O of g of n and big omega of g of n, meaning g of n is both an upper bound and a lower bound on f of n. Now remember the definition for an upper bound. If f of n is big O of g of n, then f of n is less than or equal to a constant c1 times g of n. Now if at the same time f of n is big omega of g of n, then f of n is greater than or equal to a constant times g of n. So what happens, and of course this is true when n is large enough, and in particular it must be large enough for both the big O and the big omega relationship, so it must be bigger than the maximum of the two witnesses k1 and k2 for those two relationships. But the important thing to realize is that when f of n is Big-Theta of g of n, its graph, if you want to think about it graphically, is basically sandwiched between a graph of g and another graph of g, where the only difference is which constant you're multiplying g by. So we say that f of n is of order g if it grows at approximately the same rate as g of n up to a multiplicative factor. Now, by the way, notice how we dropped all of the absolute value functions here because, as always, we consider all the numbers to be positive. Now, let's make an observation based on this definition. If f of n is Big-Theta of g of n, it's essentially the same as saying that f of n is big O of g of n and g of n is also big O of f of n. Notice this conjunction here is almost the same as this one. This part is the same. And here, instead of saying f of n is big omega of g of n, we use the reverse that we studied before, saying g of n is big O of f of n. So again, what this is saying is f of n is Big-Theta of g of n, then g is an upper bound for f, and f is an upper bound for g. Basically, they are growing at approximately the same rate. So now let's turn to a few theorems that pertain to the Big-Theta notation. The first one, which is the third one in this lecture, is simple. It says, for any function f, f of n is Big-Theta of itself. Well, clearly, if you take the constant C1 and the constant C2 to be equal to 1, and if g of n is equal to f of n, then this inequality holds for any value of n. So any function obviously is of order itself, or is big theta of itself. That's not very interesting, but it could be useful to remember. The next theorem, theorem number 4, states that if you have two functions, f and g, if f of n is big theta of g of n, or f of n is of order g of n, then it's also pretty intuitive that g of n is also big theta of f of n. In other words, if f of n is of order g of n, then g of n is also of order f of n, because both functions grow at approximately the same rate, by definition. Now, I'm going to conclude this segment with a series of theorems that we're not going to prove, but they are pretty intuitive and definitely useful. So theorem 5 states that if f of n is big theta of g of n, and g of n is big theta of h of n, then f of n is big theta of h of n. In other words, if f of n grows at about the same rate as g of n, and g of n grows at about the same rate as h of n, then by transitivity f of n is of order h of n. And this basically follows for the transitivity of the less than or equal relationship that is part of the definition of the big theta notation. Theorem 6 states that if two functions f and g are proportional, meaning one of them is equal to a constant, a real number alpha times the other one, then f of n and g of n are the same order. In other words, f of n is big theta of g of n, and of course, according to a previous theorem, g of n is also big theta of f of n. So you can multiply a function by any constant. You always get a function that grows at about the same rate. That's because that constant will be absorbed in the constant C1 and C2 of the definitions of the big theta notation. A corollary of this theorem states that the logarithm base a of n as a function is big theta of the logarithm base b of n, whatever the bases a and b are, as long as they are greater than 1. What this is saying is that it doesn't matter what the base of the logarithm is, the logarithmic functions all grow at about the same rate. This follows from a property of the logarithmic functions, which we studied earlier, namely that these two functions are proportional to each other. And therefore this corollary is a clear consequence of the previous theorem. Theorem 7 states that if f of x is a polynomial function of degree n, notice x is a variable and n is a constant, that is the degree of the polynomial, then f of x is big theta of x to the power n. Now we already know that f of x is big O of x to the power n. In other words, x to the power n asymptotically dominates a polynomial function of degree n. And it also happens that x to the power n is asymptotically dominated by f of x. That is, we have both the big O and the big omega relationship between f of x and x to the power n. And therefore, as a result, f of x is of order x to the power n. So what this means is that in a polynomial, the largest power of x is the term that dominates the rate of growth of the whole function. Now, theorem 8 states that the function log of n factorial is big theta of n log n. Again, we already proved the big O part of this relationship, and it's also possible to prove the big omega part. So remember that n factorial grows extremely fast, but when you apply the logarithmic function to it, you get a function that grows reasonably slowly. Remember, n log n grows slower than n squared. Theorem 9 is about the function f of n defined as the sum of the first n integers, 1 plus 2 plus 3 plus ... plus n. Notice this sum is a function of n. It increases as n gets larger. And this theorem states that this function f of n is of order n squared. We're going to prove this result later, and make sure you remember it because it is very useful and very important for us in this course. Now, theorem 10 is about a slightly different function. F of n here is defined as the sum of the first n squared integers, 1 squared plus 2 squared plus 3 squared plus dot 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 plus n squared. Now that function also grows with n, but it grows faster because every time we're adding a larger number, namely a square. And this theorem states that this function f of n is of order n cubed, which grows faster than the previous function. So you should see a pattern developing from theorem 9 to theorem 10, and this pattern will be made explicit in the next theorem. In this case, f of n is defined as the sum of the first n rth powers of the integers. In other words, 1 to the power r plus 2 to the power r plus 3 to the power r plus dot 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 plus n to the power r. Now this function, according to the theorem, is big theta of n to the power r plus 1. The first observation is that if r is equal to 1, then we get theorem 9, and if r is equal to 2, we get theorem 10. So these two theorems are special cases of this more general theorem. And the second observation is that this theorem only works when r is different from minus 1. I will let you think about what happens when r has the particular value minus 1. Now finally, theorem 12 states that the function f of n defined as the first n plus 1 powers of a, where a is a constant different from 1, namely f of n equals a power 0 plus a power 1 plus dot 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 a power n. Well, this function is also a function of n, and the theorem states that it is order a to the power n plus 1. Again, I will let you think about what happens when a is equal to 1.